Hey everyone, and welcome to today's Explainer. Today, we're diving into a genuinely fascinating and absolutely crucial area of modern software engineering. We're going to be exploring Chapter 20 of Ian Sommerville's software engineering textbook, and we'll be focusing specifically on the Introduction to Systems of Systems, as well as Section 20.1 on system complexity. My goal for this session is to guide you through these concepts step by step, exactly like we would in a university lecture, to make sure you build a rock-solid foundation for both your coursework and your exams. All right, let's dive right in. Here's our roadmap for today. We'll be following the textbook structure closely. We'll kick things off with an introduction to megasystems, then look at the characteristics of an SOS, move on to understanding system complexity, unpack the 3 types of complexity, and finally wrap it all up with a summary and some targeted exam prep. Okay, part 1. Introduction to megasystems, and really, the big question of why modern software projects still manage to fail. So think about it. The progress we've made in software engineering over the last 50 years has been, well, it's been absolutely astonishing. Since the 1960s, our technical skills, our programming languages, our developer tools, they've all evolved dramatically. And yet, despite all this incredible progress, large projects still run late, they blow past their budgets, and sometimes they just fail completely. Now, you might be wondering why? Well, it's not because we've forgotten how to code. It's because of the sheer massive scale of what we are now being asked to build. We aren't just building standalone pieces of software anymore. We are building compounding megasystems that integrate dozens of previously separate complex technologies. To really wrap our heads around this, we need to start with a crucial definition that you absolutely must memorize. What exactly is a system of systems, or an SOS? In software engineering, a system of systems is defined as a system that contains 2 or more independently managed elements. Now, pay close attention here, because the defining feature isn't just its massive size. The ultimate defining feature is that there is no single manager for all the parts. Different parts of the system are governed by completely different management teams, different control policies, and entirely different rules. Let's anchor this abstract theory with some real-world examples straight from the textbook. Take a cloud management system. It might be handling local, private servers while simultaneously managing public cloud servers over on AWS or Azure. No single person or team controls both of those environments. Or consider an online banking system handling loan requests. To work, it actually has to connect to completely external credit reference agencies to check applicant data. Another classic example is an emergency information system linking police, fire, and ambulance services, each of which has a totally distinct command structure. Even a university digital learning environment like iLearn is an SOS. It pulls together separate systems like Microsoft Office 365, a virtual learning platform like Moodle, and external digital archives. It's all connected but independently managed. Moving on to part 2, the characteristics of an SOS, based on Mark Maier's essential framework. Definitely flag this section in your notes, as it is a highly likely exam topic. Back in 1998, Mark Maier laid out 5 essential characteristics that define a system of systems. The first is operational independence. This basically means the constituent parts of the system aren't just useless puzzle pieces on their own, they actually operate as useful, fully functional systems in their own right. Second is managerial independence. And remember, this is the big one, the ultimate defining trait. The parts of the system are owned and governed by entirely different organizations or divisions following completely different rules. Third is evolutionary development. Simply put, an SOS is never truly finished in a single neat project timeline. It continually evolves and morphs over time as its constituent systems are inevitably updated, patched, or replaced. Maier's fourth characteristic is emergence, and this is a really fascinating one. It means that entirely new behaviors and capabilities only appear after the separate systems have been integrated. You honestly can't always predict how these pieces will interact until they are actually talking to each other. And the fifth is geographical distribution. The elements of an SOS are usually physically spread out and connected over externally managed networks like the internet. As you can probably guess, this drastically complicates both technical communication and, crucially, security. Now, Ian Sommerville, the author of our text, adds 2 further characteristics specifically for software systems. First, he points out that they are data-intensive. An SOS relies on and manages absolutely massive volumes of data, which is often far larger and more complex than the actual code of the systems themselves. Second is heterogeneity. Over a lifespan of, say, 20 years, a large SOS will inevitably become a giant mix of old and new technologies. The different systems are highly unlikely to be built using the exact same programming languages or design methods. They are fundamentally heterogeneous. So, we know these megasystems are massive. They're distributed, and they're independently managed. But before we dig into the specific types of complexity this creates, let's just take a natural breather and ask a very fundamental question. What exactly makes a system complex in the first place? That brings us to Part 3, Understanding System Complexity, covering Section 20.1, which is all about relationships over components. The absolute core concept you need to grasp here is that complexity is not just about having a high number of parts. Rather, system complexity depends entirely on the number and the types of relationships between those elements. Let me put that into simple English for you. If you have a system with 10 distinct parts, but only 5 simple connections between them, well, that's a relatively simple system. But if you take a system with those exact same 10 parts, and now you have 50 intricate connections crisscrossing between them, that system is highly complex. The raw number of parts didn't change at all, the relationships did. Furthermore, the type of relationship matters immensely. We have to meticulously contrast static versus dynamic relationships. Static relationships are planned. You can analyze them directly just by looking at the source code or a structural model. For example, knowing that component A uses component B. Dynamic relationships, however, are a whole different beast. They only exist when the system is actually executing, and they're based on runtime inputs. Think of a simple if statement in a program. Component A might call component B, but only if a specific user input actually triggers that rule. Now, this is a spot where beginners often trip up, so just remember, dynamic behaviors only emerge when the program is actually running. All right, Part 4, the 3 types of complexity. We are categorizing the chaos beyond the code, because as these dynamic relationships scale across independently managed networks, the complexity compounds massively into 3 distinct pillars. The very first pillar is technical complexity. This is derived directly from the intricate relationships between the different software and hardware components of the system itself. Now, I want to reassure you right here. This is the traditional software engineering challenge you're already very familiar with. It's the day-to-day difficulty of making sure the code compiles, the databases sync properly, and the hardware actually communicates. But as we look at how production and management processes scale, just visualizing it helps immensely. You've got the complex system being produced at the very bottom layer, right? But then that system interacts dynamically with the management and production processes attempting to govern it from above. The actual human beings managing the system have their own intricate webs of relationships and dependencies. This really highlights how complexity scales far, far beyond just the technical boundaries of the code. So let's examine those next 2 pillars, which, by the way, are a massive exam focus. You absolutely must be able to strictly distinguish between managerial complexity and governance complexity. Managerial complexity is all about people coordination. It's the headache of coordinating different managers across different organizations who all have totally different priorities for the system. Governance complexity, on the flip side, is about legal compliance and rules. It is the absolute nightmare of dealing with different national laws, privacy regulations, and corporate policies. For instance, if you're hosting data in a system that spans the US and Europe, you have to navigate wildly different data privacy laws. That right there is governance complexity. Now, let's pull all of this together. When we map out how Maier's characteristics trigger these different complexities, it really clicks into place. Notice how geographical distribution complicates literally all 3. It's technically hard to network, it's managerially hard to coordinate people across time zones, and governance is a total nightmare across borders. Also, notice how managerial independence inherently creates both technical and managerial complexity, largely because different independent teams might stubbornly use different software tools that completely refuse to talk to each other. Which brings us to our final section, summary and exam prep. We've covered a tremendous amount of ground today, so let's quickly lock in this material so you're ready for your tests. Here is your absolute must-know checklist for your revision. First, be able to clearly define a system of systems. Remember the keywords, independently managed elements. Second, you need to be able to list Maier's 5 characteristics, from operational independence right through to geographical distribution, plus Sommerville's 2 additions, data-intensive and heterogeneity. Third, be ready to contrast static, planned relationships with dynamic, runtime relationships. And finally, clearly differentiate technical, managerial, and governance complexities, making sure you don't accidentally confuse people management with legal governance. Which leaves us with one final provocative thought. We know that conventional, traditional software engineering methods fail on these megasystems precisely because of this massive compounding complexity. Reductionism, the old idea of just breaking a big system down into smaller, predictable parts, well, it simply doesn't work when the parts are independently managed and constantly evolving. So, how exactly do we engineer them? Well, that exact dilemma leads us perfectly into the next topic of your course, reductionism and SOS classification. Keep that question in the back of your mind as you study. Thanks so much for joining me for this explainer. Best of luck with your revision, and I'll catch you next time.